Let's do some math with specific heat and taking something through phases. The first thing I want to do is look at what I've been given. And I have a bunch of information written down here. We'll talk about where that came from. But the question that I have posed is, if I have benzene at 500 degrees C and want to take it to negative 150 degrees C, what is the change in enthalpy for that temperature change, if you will? And the first thing you're going to do is look up table values for this. You want to know what its melting and boiling points are. And then you want to know the energy for any of the phases that you might deal with. Now look at this. This is pretty high, 500 degrees C. If I look at its boiling point, well, that is the point where I'm going to bring it from its liquid to its gas phase. So anything above this 80, so from 80 to this 500 degrees C, then that is all in gas phase. So I'm going to start off in gas phase, get it to the point where it starts condensing to its liquid phase. So at 80 degrees C, that's where this is happening. This is that plateau in my diagram, okay? So now I am going through gas to liquid, no temperature here, but I am in kilojoules per mole compared to joules per gram. So that's important to pay attention to. Then the next thing I'm going to do is, okay, now I'm in liquid phase, and that's at 80 degrees C all the way to 6 degrees C. So my specific heat of liquid will go from 80, not 79, from 80 to 6 degrees. So that temperature range, then, I will be in a liquid. At 6 degrees C, now I'm going to convert to my solid. So this is the delta H of fusion. So it goes for if I'm melting or solidifying. So if it's going from a gas to a liquid, I'm sorry, from a solid to a liquid or a liquid to a solid, it's the same energy, just different sign. And then finally, from 6 degrees C to negative 150 degrees C, well, that's all solid. So all I'm doing is cooling by quite a considerable amount this solid benzene. I mean, real life, who would do this? Who knows? I made up the numbers, and I'm not very fond of them anymore, but we'll go ahead and use them because they're there. Okay, so the first thing I do for myself is kind of organize. I've already kind of gone through here. I'll make myself a little table and say, okay, I'm going to start at T for my gas and make myself a little thing here and say, okay, I'm going to go from 500 degrees to this 80 degrees. That's going to be my delta T. And then my next one is going to be my delta H of vaporization. And there's no temperature change there. Then my next one is going to be T liquid. Now I'm in my liquid, and that is going from 80 to 6 degrees C. And then let's see, now I'm going to go to another line where I am now fusing, so I'm going into my solid state. So here is my delta H of vaporization. And then the next one is now I'm cooling this solid. So I'm starting at 6 and going to negative 150. Cool. So the total temperature change here is going to be the 150 plus the 6. The total temperature change here is because I'm going this overall negative 150. Temperature change here is just going to be the difference in those two temperatures. So 74. No temperature change for, whoops, fusion, not vaporization, fusion. No temperature changes for either of my phase changes, but I do have a temperature change for my gas, cooling from the 500 to the 80. So this delta T will be 420 degrees C. Now I can do some math with it. If I have this, then I know that I'm going to have, let's see, 1, 2, 3, 4, 5. 5 things that I need to add together. If I don't have 5 things, I need to stop and check my work because I skipped something. Let's see what's going to make our life easier. I think perhaps what I'm going to do is go ahead and convert, I don't know, my moles to grams. That seems easiest. So let's go ahead and make a little line over here. I have 250 grams. 250 grams times 1 mole has 78.11 grams. So that's going to give me 250 divided by 78.11. So I have 3.2006 moles. Why am I carrying that many sig figs? Because even though this only has 2 sig figs, when I'm doing all my math to avoid any rounding errors, I always suggest carrying like 3 or 4 at least after your decimal, and then round in the very end so I don't have any rounding errors. So why am I doing this? Because when I get here, that way I don't forget at least to make that conversion. I can leave the kilojoules because I'll tell you what our final answer is going to be in terms of kilojoules. So leaving it as kilojoules is fine, but to make sure I'm actually working with the same thing, if I go mole to mole here, right out of the gate, that's going to leave me something in terms of energy. So these things working in terms of grams will give me joules. Okay, so I'm going to have energy here and energy here, but just a different order of magnitude. I can deal with that in the end. So see what that looks like. See my total enthalpy change. It's going to be the sum of all of the changes. So I'm going to just do a sum of all energy changes. What I am going to caution you on here is your signs. This is losing heat. That means the energy lost from benzene's perspective is going to be a negative sign. But all of the steps are negative. So don't deal with your negative or positive signs until the end, and then go back and remind you guys. So this is losing. So its final sign is negative. I'm done there. Everything else is just going to be a sum of all of the individual parts and pieces that are happening here. So let's pull that together. So I have my gas to my vaporization. So T of the gas, I've looked up here. Let's see, where's my gas? I have this Q is MC delta T. And my delta H is going to equal my moles times my H of fusion or vaporization. These get me both in terms of energy. So going from my gas, just in a gas, I'm in that phase. I'm going to use this C, the specific heat for the gas. Let's do that. The color you can actually see. So here's my C of my gas. Let's see, my mass is 250 grams times the C of the gas, which is this 1.1 joules per gram degree C, times the delta T. Well, the delta T is 500 minus 80, so 420 degrees C. Notice no negative sign. Don't do the delta T is final minus initial, so this becomes a negative sign, and then suddenly you're subtracting this and adding in your delta H's. Don't worry about it. Leave it all one sign. We're going to take care of that in the end. It's going in one direction, not in two, so they're all going to have the exact same sign. I'm emphasizing that for a reason. So now we're going to get to our delta H piece, and our delta H is this 30.8 kilojoules per mole times, well, we did the math for how many moles, 3.2006 moles. And then what next? Now my liquid, so my 250 grams times my specific heat for the liquid is this 1.8 or 1.7 joules per gram degree C. Times, let's see, what's happening at my liquid. We said my temperature range is this 80 to 6 degrees, so that's 74 degrees C. Cool. So I have my MC delta T. Now I need to go into my fusion. So there's my 10.6 kilojoules per mole times, let's see, my 3.2006 moles. So now that's 4 pieces. I have the last piece, which is just to cool the solid. So I have 6 to negative 150. So we've said that's 156. So again, I have my 250 grams times the CP for the solid is 1.1 joules per gram degree C times 156 degrees C. And there's a couple things that you can do to save yourself some button pushing. One of those is to add them up individually, and the other one is to look at this and say, I can factor this out. I can like look at all these CPs in terms of what's happening in those phases, because that 250 is going to come out. So I'll have this. I'll have 250 grams times 1.1, whoops, 1.11, that's a 1, joules per grams degree C times 420 plus 1.7 times 74, dropping my subscript, sorry, or my units, sorry about that, 1.1 times 156. Cool. And then the other one, well, those are just kind of individual because, well, we could pull out the moles. So 3.2006 moles times 30.8 kilojoules per mole plus 10.6 kilojoules per mole. Cool. That just saves on some of the button pushing. And when this gets really involved, sometimes this is just kind of an easier way to go. Other times you might want to go along with just using like step-by-step, just number push each. What I suggest you do is do it at least a couple of times to double check to make sure you haven't made any mistakes. And then the drum roll for this is, if I button pushed it correctly, I get negative 322 kilojoules. Let's check my sig figs real quick, because I feel like that's too many. So if I told you it was 250 and I didn't do a decimal for that, then that is too many sig figs. 250, so this should only have 2 sig figs. And we're done.